So coming earlier doesn't help. Technology doesn't start working better. So triple goal. First, we may want to agree on next presentations. So why we want to do that? Why do we want to do presentations? As you may have seen from the homeworks, it's even if we help each other with liberal grading, it is objectively hard thing. And if you do presentations, then it's always a good boost to grades. And from cynic point of view, from more global goal to get deeper into physical chemistry, learning by doing is always better than just academic listening and memorizing things. And learning by doing through numerical exploration is much more efficient than solving problems. Enough motivation, should I design something new? So I will distribute something that you have copies for to get through the list of this stuff as we speak. And today I put it on the other part of table so that everyone each time has equal opportunities to start and get the chance to select choices. So the plan is to make focus on.
I have a question.
Yes.
Are we signing up for the big bold headlines or the smaller?
I will explain. I will explain in a smaller.
Okay.
Smaller. I don't know if focusing on the screen will help anyone. It's really like teasing. So I'll show. Okay. So there are several chapters of style of presentations, same as last time, 3 minutes. We did really well. We fit a dozen of presentations into 50 minutes, and we need to repeat this main goal next time again. When? In week and a half, on Friday, October 27th. Subject of presentations, the code for propagating not an eigenstate of quantum system. And right now, we are doing it last Wednesday, this Wednesday, and next Wednesday. So it is not as, although it is longer, the code is longer than things that we did before, it is not very long. It's just four pages, and we do not need to understand each line, just general idea. So right now, the code works for, well, is tuned to describe boring particle in a free space, but it can be with one line change tuned to any one-dimensional system, what we will do in later times. So before we try to apply it to something more interesting and advanced, we may go through the code, run it at limiting cases, and see principles, how it works, how we can save output of what it generates and make ourselves comfortable. Since, well, it is always more efficient if you split responsibilities and one person becomes expert in one aspect and teaches others. Main goal, too many main goals. Side goal is to share personal experience, not academic knowledge from highly respected Wikipedia, but just share what you see as a practitioner of this code, like your story of success and failures. Like, I did this, it did work, or I did this and it didn't work. So please try to sign for more than one. I will respect your opinion highly, but reshuffle it so that it goes smoothly one after another. And some subjects can be merged or split, and it will be much easier for me to arrange them logically after I see your opinions. So if you count number of subjects here, it is larger than number of people in the class. So there is a chance that some of them will be missed. The logic of this material is that going through several chapters is just for logics, because if I start reading out loud, each of them will be too long. So this code, if you were not attending the night or whatever evening session, the code neglects the standard approach of eigenstate expansion. So it doesn't use concept of eigenstates at all. So it is going back to propagation with evolution operator. And there we model all operators that contribute to evolution operator in some numerical form. So you can select, and we covered it in the last lab Wednesday. Then there are several questions about how to use these operators after they have been set up to predict future of an event. So how to set up initial conditions, how to see, check that it is normalized, how to see that it propagates forwards, not backwards in time, something like this. So another chapter. Then, since our goal in the course, and for some of us even in the life, is to predict observables, and the code does it. So there are several questions about how the code converts wave function that it computes at any time step into observables. And since we are going to look at several practical examples and represent their observables or shapes of wave packets to each other in our future, we may focus on the ways to visualize and make movies of whatever this code is predicting. I know that one of you was presenting on making movies, but now I don't know who will select it this time, but it is one step more. Upload it to YouTube so that you can share it among each other. And I think one of the future homeworks will have uploading YouTube videos instead of bringing in written works. And then, if no one is excited by this stuff, there are attempts to apply this code to some, I wouldn't say practical, but more realistic systems. And basically, this part was covered last Wednesday. This part will be covered today at half, and this part will be covered next Wednesday before your presentations. So I would be very curious to have the field sign up list by the end of the meeting. So I hope you, yes?
Sorry, just going back to that quickly. Is the WP code the code that is like the 4-page thing?
Yes.
Okay.
Wave packet.
Wait, okay. Thank you.
So I hope everyone has brought the hard copy version of this assignment, and I owe you to return the previous homework, which was based on MATLAB, but you shouldn't worry too much. You performed very well, and there will be not much of critical feedback here. Let's better focus on this theoretical work right now. So about the grades. So in previous and in this homework, the extra credit, the most complicated thing is extra. So if you did everything by 100% except this, you are safe. So this extra credit is designed in order if you fail in something simple, but you are a congenial solver of advanced problems, you do not miss your credit. Like maximal grade is 100%, but if you do extra credit, you will get 140. So how do we do? How do we arrange our effort? I think let's practice some cryptography symbols again. So please design a symbol that you think represents you. Write your name nearby and add this sticker to your work. This. Oh, I do not want to have them. I want you to distribute them among your peers.
Okay. Yeah.
We owe to increase time assigned for rest and sleep. Bit pressure.
I think my number 2 is pretty screwed up. Yeah. I thought it was golden when I did it. But then when you touched me, I looked at it again and I was not. I was like, oh shit. This is all broken. Next week's live, I'm happy to do that. We call it this is going to take a little bit longer than this.
I know that I'm not very efficient cryptographer because you're passing by this list and you can learn who's who. But I will work in designing some efficient algorithms of encryption.
That's how I heard I got something big. I got really? I don't think we were supposed to stuff like oh, okay, that's just an issue for me. They use like TV and what I have the mass in terms of megawatts like choose for it. So then I just use kilograms. I convert EV to joules. One conversion into so which one makes more sense? Nanometers or less than 2 meters?
I'm trying to use this too.
That's like the difference between energy states and atoms, isn't it?
Let me help you certain works.
Because I'm thinking like, I guess we'll find out.
I want one.
You have this one?
Yeah, we're mixing shirts really mixed up.
No. I can't Matthew correct him now.
Yeah, I just did some.
You're not gonna get corrected out here. Dude, you're not gonna figure out where exactly you're gonna use. I'm not gonna shoot up your first one.
Got anything to grade? You already got something to grade? That's. Huh? Let's exchange. Do you have something?
Yeah, I got
One
something.
page.
So that to break the trend. Anyone, please lift hands who didn't got exchange of homeworks. I was trying to bring disorder to the system, but
Maybe they're trying to do
so if you still have your personal homework in front of you, please lift your hand. It means that you all have exchange, right? So I'm going to go through the assignments and share my opinion of how they should be done. But you're already growing as scientists, and you may have better ideas right away. So for question number 1, I even didn't include it into the key. So what we are supposed to do is to write E1 h squared I squared 2 n equals 1 squared divided by L squared and solve for L. Telling that L is square root of all this square h bar squared. And 1 over E1. And then you plug E1 and get the size. Right? It is what if you see this equation, and even if the answer should be in reasonable size of about like 20 angstrom. I don't recall how it was plugged in the numbers, but if the equation is right and the size is a little surprising, still give like 9 out of 10. So the equation is more important.
Really?
The question number 2, which is worth of 30 points. Again, try to be liberal, help each other. We are not going to put anyone down. So for first and last, one doesn't need to be big mathematician. So we just normalize. Do not write anything. If the function is homogeneously distributed between 0 and 1, and we need to find an average position, what is the expectation value L between 0 and L? Expectation value of the position will be equal L over 2, right? So here should be L over 2, and for the second state will be L over 2 as well. So it is already whatever 25% of a grade. But for expectation value of position between 1 and 2 and 2 and 1, they should be the same, right? So you need to find only one of those. And this does coincide very much with extra credit question from 2 weeks ago homework, right? So I should admit I wasn't doing this homework at the same time as you. I did it a couple of years ago. But as far as I remember, the problem of taking this integral is that, well, here's my answer. And if you see the right answer or something that reminds it, just give full grade and go to the next problem. If the answer is strange, then one can go over details. So products of trigonometric functions is always hard to integrate. So the product can be replaced to summation by equations that you can find in Wikipedia, in the deepness of our memory, or derived via Euler equation. So we keep x, and here, instead of product of two functions, sine of 2 pi x and sine of 1 pi x, one can get the cosines of the summation of these two arguments and subtraction of these two arguments. So subtraction 2 minus 1 will be 1, therefore cosine of pi x, and summation of 2 plus 1 will be 3, so 3 pi x. And then one can consider it as two integrals. One of x times cosine, and another is x times you recall this rule of differentiating the product, right? Integration of function u with the derivative over function v is product of these two functions minus integral over the function and thing under differential as well. And here we are considering that thing that we want to put under differentiation is what? It's sine. And then first term gives 0, and second one, I'm a little bit lost in my own things, but integration of cosine is expected to give cosine is expected to give one limit and minus one another limit, so this will be 2. And then we just keep track of all the factors. And here, if it is even or odd number, then the difference on upper and lower limits will be either double or 0. And since we have the n equals 1 and 3, there will be two non-zero answers that we add together and get something of the order of L length of the box divided by 5 if we plug in the numerical value of pi. Good. So the protocol for finding expectation values of P, matrix elements of P, is just plugging in the differential operator, differentiation, right? And then it will be easier integrals. There will be no x, it will be only the product of two trigonometric functions that you can take. So if you see the replacement of P to this minus I h bar d dx and then something reasonable, just give full credit. Question number 3. This cannot be done without, well, the question number 2 was a preliminary step to complete question number 3. You will use the matrix elements towards this answer. And here, well, this year it was I in this place. But what you are supposed to do is to do similar, well, one can get the right answer by many alternative ways, but the quickest way is to get the expectation value in the same way as we did in class. So the split part that depends on position and part that depends on time. So for position, you just plug in the values of matrix elements that you got in previous question. And for the time-dependent part, you multiply initial values of expansion coefficients by the oscillating exponentials. And since we have the star symbols, the signs in these exponentials will be changing when you make products. So, depending the part for product of C1 and C1 and C2 and C2 will be time independent, and these 50% probability and 50% probability here, and the expectation value of position is midpoint between the walls. So the first term for expectation value of position will result in L over 2. And then there will be something oscillatory times the matrix element of the transition expectation value of position between non-coinciding states. So depending on the phase of initial condition, like if you have I or do not have I, or we still keep 50-50 distribution between ground and excited, you may get different trigonometric function or summation of those, but it will be always the same figure. So it will be oscillations around point L over 2 with amplitude which is much smaller than the size of the box, about 1/5 L. And the oscillations of position and momentum are expected to look in this phase shift. So at the places where position comes through midpoint, momentum is expected to have maximum. in the place where position doesn't change in the vicinity, momentum is zero. So you should get two functions that oscillate with same frequency but shifted by phase. So if you see functions like this, even if something is off, then you can just withdraw maybe 5 points from the overall grade and be happy, or make the person whom you are grading happy. If you do not see right answer, and if you do not see right style of thinking, then you start withdrawing points a little bit. And if the person whom you are grading just started and wrote the introductory, how to begin with, but not much, just give some points for an attempt. I don't know if I will look through everything later, but if some of you did this problem with MATLAB by using the code from previous homework, it is completely legitimate. So we care about the answer, not about the style it was obtained. The question number 4, worth of 10 points, and it is straightforward. So the number 4, calligraphy is not good. P as function of time is constant. It is equals to whatever it was at initial time. And the position, expectation value, is expected to grow linearly with this velocity. P over m should be 1 times t, right? So if you see this, p equals m, x equals t, or something similar, give either full grade or withdraw 1 point if you see some problems. Number 5. This is quantum approach to massive objects falling on the ground. Is the only thing that either axis of position is directed not up by down, or the gravitation force acts up rather than down. Right? So it is. We have direction of coordinate and potential going into opposite directions. So this is the hardest of the problems, excluding extra credit. So first thing, you do need Heisenberg equations of motion that you may just take from lecture notes. And if you do not have it, then you are expected to kind of derive it. Right? And so we have the general Heisenberg equation of motion for any operator, commutated with Hamiltonian. And then I'll show it in a minute. If you already have it, or a person whom you're grading has it, just skip it. But I will repeat details. So if you need commutation of Hamiltonian with position, you exclude potential energy from Hamiltonian for this example only, because the potential is polynomial of position, and position is polynomial of itself. So it will commute, they will commute to each other. So you need just a commutation of kinetic energy operator with position. And if you carefully do it, you recognize that it will be momentum operator. So commutation of Hamiltonian with position will be more momentum. So it is equation number 1. And then you go logically that in contrast to previous problem, we do not have guarantee that expectation value of momentum will stay constant. It may change, right? So our P expectation value may depend on time, and then we need an equation of motion for ddt of P. And if we do want to derive this equation, and we do not see it in notes or in respect for Wikipedia, then you just plug in letter P in the Heisenberg equation of motion and start practicing commutations. So here, the kinetic energy is a polynomial of momentum of P, and momentum is polynomial of itself. Therefore, they will commute, and you can remove it from Hamiltonian. So you basically need commutation of potential V with momentum. And you cannot simplify too much by this point. Then you need to plug in the explicit you can make this commutator, apply the rule of differentiation, and see that in second term there will be two terms. Two of them will compensate, and then you have the derivative of potential over position staying on the right side of Heisenberg equation of motion. For those of you who are exposed to physics education, you can see that it is a gradient of potential related to force. So it is, to some sort, it is self-evident equation, but now it is derived in quantum way. Now, if you do have the potential set up as proportional to first power of position, you take derivative, take care of signs, and you see that it will be constant. So derivative of momentum is constant, but momentum itself is not. Then, so it is a set of equations that you solve, and first you solve for momentum and see that it grows linearly, same as we drop something, accelerates, or if we put pedal to the metal. And the position grows as a square of time. So same as in classical mechanics, but same equations are derived through quantum machinery. Be liberal. In grading, try to put as much points as possible. And if you do not see some of these steps, just put question marks and write something fluent, like next time you'll be able to do it. I do have key for the number 6, but we will run out of time very soon. I better start next section of lecturing, otherwise we will not finish the course in time. So if you can, please add grades together. Let me briefly show for extra credit. Only the answer. So it should be, again, two oscillating functions of the same frequency, but they should be in the off phase. And if someone shows picture of parametric plot where one function and second function are plotted as two functions as parameter of one argument, then give full grade without looking onto any equations. And if something is missing, just give benefit of the doubt. So if you have time while I'm walking around and collecting, please add numbers But if you do not have time to it, I'll agree to do this little arithmetic practice. We're still practicing arithmetic?
Yeah, I'm not good with that.
Oh, definitely.
Anyone I'm missing?
What would you do if I compete?
Okay, now we do have about 5 minutes
I would buy you a
for the actual lecture.
But you can't be drinking like Bud Light, Coors
Oh,
Light.
yeah, I know.
Yeah, no, you gotta drink real beer.
I gotta get like a lager or a porter or something. Am I allowed to have a partner?
Yeah.
Okay.
Well, yeah, because I had one other person.
Okay, just wanted to clarify.
So, what do we start? We start vibrations. So not only electrons, but also nuclei, especially light nuclei, like protons, hydrogens, oscillate, but they are so small that they are uncertain where they are in position, and quantum laws do apply to them. So, how do we start thinking about it? Well, anything in chemistry is changing distance between ions, between atoms, forming a bond, coming together, or breaking a bond, going apart. And then any reaction can be accumulated as set of sequence of these events. So we are starting next row in our map. We're done with free electron, with box, and now we go into HO, which is not a handout, it is a harmonic oscillator. So position of atom A, say R capital sub A, origin, position of atom B, and then distance between them, R A minus R B. Absolutely. If they interact, it means that the potential energy changes when the distance between them is changing, right? How does potential energy change if they bump into each other and they do not want to fuse, if they repel? Like if they feel force against each other, if they need energy to approach closer. So if I want to climb up, I need energy to do it. So the energy, potential energy increases if the distance contracts. If two atoms are attracting each other, but by some reason someone wants to pull them apart, energy again increases, right? So if we make this axis RA and RB difference, on both sides, when they go apart or they go too far together, there should be increase of potential energy. And somewhere in between, there should be a sweet spot where energy doesn't change if distance between atoms changes a little bit. So it is interatomic distance in stable molecule, and it is an equilibrium point. Right? I didn't make a big discovery. Typically, if they go too far on the infinity, the potential will be zero, but if they try to approach to the same spot, the force becomes infinite. So the description of the motion of two atoms close to each other, and we are not limited to two atoms only. There is a so-called concept of normal modes. If you are exposed to infrared spectroscopy, you know that there is a collective motion of atoms. They all collectively contract or expand at the same frequency, and same treats, same approaches are reasonable for multi-atomic molecules. But now we are just, for a simple picture, consider two. Diagram. If the interatomic distance is very, very close to optimal distance, to the equilibrium point, then the potential can be represented as RA minus RB squared with some constant. U equals. And this is the main message of today's lecture. If you want to be meticulous, we may recall the interpolation expression from calculus, that any function can be represented as, can be expanded in Taylor series with position at some point, then first derivative times elongation from equilibrium plus second derivative times elongation from equilibrium squared, and so forth. Although it is possible to expand to infinite number of terms, lazy and wise people stop at second or third term because it is too complicated to go and doesn't give much insights if one go further. We will be super wise and super lazy, and we will stop at second term. In case we know for sure that we are at the equilibrium, which means value of position at point R and at position R plus delta R will be the same, which means the first derivative will drop, right? Therefore, we automatically neglect. The value of this point can be kept, but if we add or remove constant to Hamiltonian operator, nothing will change in the law of motion, nothing will change in quantum observables, nothing will change in the future. So we can arbitrarily add or remove. So we'll drop this term as well. And here we'll have the square of the distance from equilibrium and second derivative of the potential energy surface. What else? There are rumors that Sir Isaac Newton hated all scientists who were working in British Academies of Science before them, up to burning their portraits. I think it is not right. It is only rumors. But the person who developed Hooke's law, how the ball in a spring, there are no his portraits, and there are rumors that last portrait was burned by Newton. So the linear force is linear to elongation, potential energy is squared, and one can use two concepts: the rigidity of a spring, the Hooke's constant, okay, and mass of a ball, or reduced mass if it is diatomic. And if you remove it from equilibrium and let them go, they will oscillate with frequency, which is square root of this Hooke's constant over the mass, right? Probably it's not a big secret for you. And then one can work on the potential energy with this k r squared over 2 and replace it according to this to frequency squared mass over 2. And then if you accept it, then the Hamiltonian for quantized oscillator you include standard kinetic energy plus potential energy, which is proportional to square of the elongation and this mass times frequency oscillations. Enough for today. see you at 5 p.m. today in the web. If you are enthusiast of the wave packet propagation.
Oh my god. Yeah.
So you get that.